In all of our previous videos on infinite series, we had one of two conclusions about an infinite series. Either it converged or it diverged. What we are going to do in this lesson is take the notion of convergence and add a little bit more description to it. So there are two ways for a series to be convergent. Either it's absolutely convergent or it's conditionally convergent. Let me talk through both of these definitions now, and then we will look at a lot of examples. I'll explain more about that at the end. Okay, so, what we have seen is that if a series has alternating signs, then it can converge quite easily. Let me see if I can actually squeeze an example here. So, consider the series that looks like n equals 1 to infinity, negative 1 to the n, 1 over n. This is the alternating harmonic series. It's quite easy for an alternating series to converge. We just need for these terms, the 1 over n in this case, to be monotone decreasing down to 0, and that's it. So this series converges. However, if I take these terms, and here the term a sub n is going to refer to the entire expression, negative 1 to the n times 1 over n. If I take this expression and I compute its absolute value, what we would be setting up is a series of non-negative terms. So the absolute value of our original series, in this case, would be the divergent harmonic series. So what we can observe with these two examples is that the divergent harmonic series, where all of the terms are positive, diverges. But when we allow the signs to alternate, the alternating harmonic series converges. So it's like by alternating signs, we get a big boost in the ability of our series to converge. So let's now look at these definitions. Okay, and I'm going to refer back to this example as needed. If we take a series and maybe the series has a mixture of positive and negative terms. It could be a classic alternating series, or it could just be some expression that kind of randomly is positive sometimes, negative other times. If I take all of the terms I'm adding up and I make them all not negative by making every single term not greater than or equal to 0. So I take the absolute value of every single term. Then I'm losing this boost that I get from having alternating signs. It's harder for the absolute value of an to converge than it is for just plain old an to converge. If, however, the series is so well behaved that when I take the absolute value of every term and add it together, it still converges, then that means that the original series was really quite convergent, is how I think about it. It's like it didn't really need this alternating behavior. We say that such a series is absolutely convergent. Absolutely here, that word absolute refers to the absolute value, but sometimes I like to think of it as like it's absolutely convergent. It's really quite convergent. It didn't need the changing sign behavior. It converged kind of on its own, if you will. So that is the notion of absolutely convergent. It's a type of convergent. So if you're absolutely convergent, you're still just regular plain old convergent. On the other hand, if your series is convergent, but when you take all of the terms and you make them all non-negative by doing the absolute value, that's not still convergent. So it's not absolutely convergent. Then that is just conditional convergence. So if a series is convergent but not absolutely convergent, it's conditionally convergent. We have an example right here. So the alternating harmonic series is convergent. This is a convergent series, but it is not absolutely convergent because when I take the absolute value of every term, I get the divergent harmonic series. So this is convergent, but this is divergent. That means that the type of convergence that this original series displays is conditional convergence. So I don't want you to get too confused by all of the different like adjectives here. We're saying that there are two ways for a series to be convergent. It's either absolutely convergent or it's conditionally convergent. We are going to do a bunch of examples in this lecture. So up next, we have two examples where we're just going to analyze them using techniques we already have. We will see what kind of convergence they have if they're convergent. If they're not any kind of convergent, they're divergent. After two examples, I'm going to introduce in a new test called the ratio test. I think this is one of the more fun tests to apply to infinite series. So after the ratio test, we will do, I believe, 6 more examples. So there's just tons of examples in this video. The ratio test is particularly good at detecting absolute convergence. So it's a great test to apply when you think a series is absolutely convergent or divergent. It's not so good with conditional convergence, as you will see in the examples that we investigate. Okay, for this first example, we would like to take the infinite series, starting with n equals 1 and going off to infinity, of terms that look like the sine of n plus the cosine of n divided by n squared, and figure out, is this infinite series absolutely convergent, conditionally convergent, or divergent? So these expressions here, or this expression, sine of n plus cosine of n divided by n squared, this is our term a sub n. I would like to test absolute convergence first. So let's take the absolute value of a sub n. That's going to be the absolute value of the sine of n plus the cosine of n divided by n squared. N squared is always positive, so I can write this as the absolute value of sine of n plus cosine of n all over the positive number n squared. Here's the thing, is that the largest value for sine is 1, the largest value for cosine is 1, the smallest values are -1 and -1. Whatever this sum is, it's between -2 and 2. So if they were both -1, it would be -2. In fact, they would never be both -1 at the same time, just mentioning that. But we could say that -2 is less than or equal to whatever this sum inside the absolute values is less than or equal to +2. So overall, this numerator is less than or equal to 2, so that the absolute value of our series terms is less than or equal to 2 over n squared. Let's fully justify everything for this first example. 2 over n squared is a convergent p-series. So if I say the series going from 1 to infinity of terms that look like 2 over n squared, this is a convergent p-series because p equals 2. That means that the series of terms which look like the absolute value of the sine of n plus the cosine of n divided by n squared converges by the ordinary comparison test because it's less than or equal to a convergent series. So let me just write the series going from 1 to infinity of the absolute value of an rather than writing that whole thing. This series converges by the OCT. If this series converges, the series I get when I take the absolute value of the terms we're adding up, if that converges, then this converges. And in fact, we can say now that it's absolutely convergent. So to summarize, the series from n equals 1 to infinity of sine of n plus cosine of n divided by n squared, it's convergent. In fact, it's absolutely convergent. Now let's look at the series whose terms look like -1 to the n minus 1 times the natural log of n over n. Once again, is this series absolutely convergent, conditionally convergent, or divergent? Let's start with absolute convergence. Okay, so let's test this first. To do that, I want to take the absolute value of these terms and see if, once I've taken the absolute value, if they form terms of a series which would converge or diverge. Okay, so let's take the absolute value of -1 to the n minus 1 times the natural log of n divided by n. Whenever you have -1 raised to a power inside of the absolute value, you can just get rid of it because that's going to be 1. The absolute value of n is n for n greater than or equal to 2. And then you might pause for a second because natural log takes positive and negative values, but it's positive whenever the input is greater than 1. That is covered in this case because we're starting with n equal to 2. So the absolute value of our series terms is just natural log of n over n. So the question now is if I take these terms and I stick them in a series, would it converge? And for that, you have to start thinking of other tests because this isn't a P series or anything like that. My mind would go to a comparison test. That's where I would start looking. Now, what would be the right comparison? Seeing this in the denominator makes me think of the divergent harmonic series. Anytime I see something over n, I'm thinking, can I compare this effectively to the divergent harmonic series? Natural log of n is greater than 1 whenever n is greater than the number e. So natural log of e is 1, and then from there it grows. So we can say that natural log of n over n is greater than or equal to 1 over n. Okay, technically that's not true when n equals 2, but the first term in a series doesn't affect convergence or divergence. This inequality is true for every other term in the series, so this is a good enough comparison. The conclusion here is that when we took the absolute value to get new terms to analyze, those terms were bigger than something which we know to form a divergent series. So by the ordinary comparison tests, the series of terms that look like natural log of n over n would diverge. Let me write that down. So since natural log of n over n is greater than or equal to 1 over n, again, starting with the second term, and this series, 1 over n, is the divergent harmonic series. Then that tells us that the series natural log of n over n diverges by the ordinary comparison test. That means we cannot be absolutely convergent. If this series does converge, it's going to need the fact that the terms are alternating. If we make them all non-negative, it's not going to converge. So the new question is, okay, it doesn't absolutely converge, but does it converge? Does it conditionally converge? Meaning, does it converge as it is with some mixture of positive and negative terms? This is an alternating series. We have that -1 to the n minus 1. To test this, we need to use the alternating series test. That just has two requirements. You need your terms to go to 0, which is like the test for divergence, and you need them to be monotone decreasing. So let's check for conditional convergence. Okay, so with the alternating series test, that's what we need to check. Let's check whether or not the terms are monotone decreasing first. So is a n plus 1 less than or equal to a n? Right here, by these terms, I mean terms of the form natural log of n over n. There are different ways that you can do this. I'm going to switch to the language of a function. So let f of x be the function whose expression is natural log of x over x. When I switch to talking about a function, I can take its derivative. So then the next step would be to say f prime of x is, and I'm sorry to be squeezing this all in here, but f prime of x is going to be low d high minus high d low over low low. So low d high is x times 1 over x. Low d high minus high d low is natural log of x times 1 over low low is over x squared. Take a moment to analyze this. We discussed in the lecture on alternating series test what exactly you need to look for in this kind of expression. So determine here what the sign of f prime of x is, and then what does that tell you about the series of terms of the form natural log of n over n? Okay, what we find is that f prime of x is 1 minus the natural log of x divided by x squared. What I talked about in the alternating series test lecture is that when you do the quotient rule, the denominator is something squared. So when you're trying to analyze the sign of a derivative with the quotient rule, you just need to analyze the numerator. So natural log of x is greater than 1 whenever x is greater than e. Yeah, natural log of e is 1, and then x greater than e, this would be negative. That's good enough. Again, that might exclude the first term, but that's not important when we're talking about convergence. For n equals 3 and beyond, we can conclude that the sequence of terms of the form natural log of n divided by n is a monotone decreasing sequence. So that's the first thing we test with the alternating series test. The second thing is that the limit of those terms is 0 as n goes to infinity. So let's do that. The limit as n goes to infinity of natural log of n over n. I am going to again switch to x because I'm going to do a L'Hopital's rule to show that this limit exists and is 0. So let me say that this is the limit as x goes to infinity of natural log of x over x. If I think of this as a function of x, where x is any number, say greater than 1, if you like, I can differentiate. With L'Hopital's rule, we can evaluate that this limit is the same as the limit as n goes to infinity of 1 over x divided by 1, which is 0 as we would need it to be in order to get convergence. Okay, so this series, as it was originally presented with the alternating signs, passed the alternating series test. Had decreasing terms, the terms natural log of n over n, and those terms went to 0. Therefore, according to the alternating series test, this series converges. It converges, but the absolute value of those terms, when we take the absolute value, it does not produce a series which also converges. Therefore, we could say that this convergence is only conditional. We need the plus and minus signs. We kind of need some canceling out, if you will. So this series is conditionally convergent. The ratio test is a test that we can use on any series to try to determine if it's absolutely convergent. We are going to do 6 examples of this. So don't try to memorize these statements yet. We'll see all of these behaviors emerge. But what we do with the ratio test is we set up a ratio between the n plus 1th term and the nth term. Take the absolute value of that ratio and then let n go to infinity. So it's the limit of the absolute value of a sub n plus 1 divided by a sub n. Again, we're going to do lots of these. If that limit exists and it's a number less than 1, we can say that our original series was absolutely convergent. That means it's convergent. It's so convergent, it's absolutely convergent. If the limit, however, is bigger than 1, then you are divergent. The original series diverged. The limit might not exist, or it could equal 1. In that case, the original series just can't be analyzed with the ratio test. We say it's inconclusive. So let's work through 6 computations where we will see all 3 scenarios play out. I again think that the ratio test is kind of fun. So you want to get into the habit of setting up this ratio. You look for certain kinds of cancellations. I'll try to bring those to light when we see them in the examples, but practice this a lot. You get really fast at it, and then it becomes a very effective tool. Okay, let's look at the series whose terms look like -2 to the n over n squared. We want to again assess the convergence of the series. Is it absolute convergence, conditional convergence, or does the series diverge? We're going to jump straight into the ratio test this time. So what I'm going to do is take a limit as n goes to infinity of an absolute value. And I'm going to write fractions inside of fractions exactly once, show you how to set that up better. And then in all future examples, anytime we have this kind of expression, we're going to go straight to the better form. So let's start by writing the n plus 1th term. That's -2 to the n plus 1 divided by n plus 1 squared. Okay, so this expression corresponds to a sub n plus 1 from the description of the ratio test. We're going to divide that by the nth term. So that's -2 to the n divided by n squared. Okay, as I said, I'm only going to write something over something over something over something once for the rest of the lecture, because what I want you to do whenever you see this kind of computation coming out of your work is realize that dividing by a fraction means multiplying by the reciprocal. So this is going to look a lot better and be easier to simplify if I write this as the limit as n goes to infinity of this fraction the way it is. So you write a sub n plus 1 kind of in the natural order, -2 to the n plus 1 divided by n squared. Then multiply by the reciprocal of the an term. So I'm going to multiply, oops, it's so easy to write the n plus 1 term and then I mess it up. So the bottom should be n plus 1 squared. Okay, there we go. Multiply it by the reciprocal of the a sub n term. That's going to be n squared divided by -2 to the n. When you do the ratio test, you look for like terms to compare. So here, n squared and n plus 1 squared, I'm going to compare those. So it would be natural to pair up this expression with this expression. Likewise, it would be natural to pair these -2 to a power term. So I'm going to kind of reorganize this expression now that I've made kind of hard to read, putting this over this and this over this. So this is going to be the limit as n goes to infinity of, let's start with the -2 powers. So -2 to the n plus 1 divided by -2 to the n. And then my second expression is going to be n squared over n plus 1 squared. This is often the case with the ratio test. You start looking for simplifications. And if you have something raised to a power, like this first expression with the -2 being raised to powers, you're going to get some cancellations. In particular, this is -2 to the n times -2 to the 1. The -2 to the n will cancel with the denominator. So what I'm going to do is cancel the denominator with that leading in there. Then here I have n squared over n plus 1 squared. You can leave that as it is. You could expand out the denominator. That's another option. This is a rational expression. So understanding the limit as n goes to infinity is really going to be looking for a balancing act between the numerator and denominator. What I'm going to do is say that this is the limit as n goes to infinity of -2, but the absolute value of that is 2. So let's start getting rid of the absolute values as well, times this expression. I'm actually going to put this into one large square term, n divided by n plus 1 squared. That's just one way to assess the second term. It's not the only way to let your mind go. Again, you could expand this, you could leave it as it is. The reason why I'm saying this is not the only way to analyze this is if you look at this as quadratic over quadratic, which means that we have the same highest powers in the top and bottom. So the limit as n goes to infinity of this second term is going to be 1. So this goes to 1. Likewise, this goes to 1 squared. That's 1. So the limit of everything is 2. But the ratio test says that if this limit is bigger than 1, then the original series diverged. So by the ratio test, our series diverges. In this example, we would like to use the ratio test to analyze the series of terms that looks like -3 to the n divided by the quantity 2n plus 1 factorial. Factorial is something that you see a lot in ratio test problems, so I'm going to show you how to handle that factorial. Let's jump straight into the ratio test. This is going to be the limit as n goes to infinity of the absolute value of, first I'm going to write the n plus 1th term kind of as is. So that's going to look like -3 to the n plus 1 divided by, let me be careful here because I've got that leading 2. So what I'm going to write is 2 times n plus 1 plus 1 factorial. Just want to make sure you end up with the right expression there. I need to divide this by the nth term, but as I just said in the previous example, I'm not going to write some massive fraction. I'm going to multiply by the reciprocal of the original expression. So that's like the nth term. So that's going to look like 2n plus 1 factorial divided by -3 to the n. Okay. We need to pair up like terms. So again, it's going to be the -3 powers or the -3 raised to powers. I'm going to match those up. I'm going to match these factorials up. Maybe write this a little bit more condensed. So this is the limit as n goes to infinity of -3 to the n plus 1 divided by -3 to the n. Similar cancellation to what we had in the previous example will happen there. What's going to happen with the factorials is often what you will observe whenever you use the ratio test to assess a series that contains a factorial expression. So let me leave 2n plus 1 factorial as it is. For the factorial of the larger number. So by that I mean that after I distribute the 2, we would be looking at 2n plus 2 plus 1. So let me write 2n plus 3 factorial. That's what this first denominator is. So 2n plus 3 factorial. Here's what you look for. 2n plus 3 factorial is the product of all the consecutive integers up to 2n plus 3. So if I start to expand this down, it would be 2n plus 3 times 2n plus 2 times 2n plus 1 times 2n times all the numbers on down to 3, 2, 1. But we can write that more concisely if I say 2n plus 3 times 2n plus 2 times 2n plus 1 on down is 2n plus 1 factorial. Like that. With factorials in the ratio, with factorials in the ratio test, you're going to look for cancellations like this. So what I got was I peeled off the first two terms so that I could get an expression which will cancel with the numerator. All right, so let's do our canceling. Ratio test usually has a lot of it. So cancel there. We'll be left with these leading two terms. Cancel the -3 to the n into the -3 to the n there, leaving us with one copy of -3. So that this is simplified a lot now to the limit as n goes to infinity of, let me just kind of rewrite everything and then we'll assess. -3 divided by these two terms. You could expand them. I'm just trying to think, is it clear if I multiply them out? Maybe. Let's do 4n squared. You can leave them factored, but I'm just going to expand this out so it looks like a nice quadratic. 4n squared plus 4n plus 6n is plus 10n plus 6. Okay, that expansion I just did in the denominator is not obligatory and some people might not find it useful. What happens here as n goes to infinity? The numerator is stuck at -3. The denominator is going to infinity. So this ratio is going to 0. 0 is less than 1. So that tells us that our original series is absolutely convergent. Let's do the ratio test on this series, whose terms look like -1 to the n minus 1 times n divided by n squared plus 4. So let's set up our n plus 1th term so that we can take the limit as n goes to infinity of the absolute value of -1 to the n plus 1 minus 1. I'll write that. N plus 1 minus 1 times n plus 1 divided by n plus 1 squared plus 4. Okay, that whole thing is the n plus 1th term. I need to multiply that by the reciprocal. So I'll do n squared plus 4 in the numerator and divide that by -1 to the n minus 1 times n. Okay, so if it's not totally clear, there's more going on here. This is a sub n plus 1, and this is 1 over a sub n. What I will say is that the negative ones pair up, but also we're taking an absolute value. So the negative ones aren't even going to matter because whether it's -1 to the n or -1 to the n plus, doesn't matter because we're going to take the absolute value. And this are going to give us 1. So you could even choose to not write them. So let's match the n plus 1 with the n, and then we'll match these quadratics as well so that this is the limit as n goes to infinity of n plus 1 over n times n squared plus 4 divided by, I'm going to leave this in factored form, n plus 1 squared plus 4. By factored form, I mean that I did not choose to expand this. If you wanted to, you could. Both of these are rational expressions, and both of them have the same highest power in the numerator and denominator. So we have n and n in the first expression, and then in the second expression, we have n squared, and if I expand this, n squared. This goes to 1, this goes to 1. The coefficients here are all 1. So overall, this product goes to 1, which is inconclusive. We need to take a look at this series for a minute. What kind of series does it remind you of? What kind of series is it? Just think about this series. Make a prediction about what kind of convergence or not. Does it diverge? Make a prediction. If you look at the n divided by n squared plus 4 part, you might realize that that feels like the harmonic series. So it's unlikely that the series is absolutely convergent. Let's verify that. So if I take the absolute value of negative 1 to the n minus 1 times n over n squared plus 4, that's n over n squared plus 4. If I knock the 4 out of the denominator, we go up in size so that I could say that this is less than or equal to 1 over n. That's not the direction I want. If I want to show that this is divergent, I would want to be bigger than something which diverges, not smaller. So the ordinary comparison test isn't going to work here the way that this is written, but let's do the limit comparison test. We'll take the limit as n goes to infinity of this divided by 1 over n, because I know that that is those are the terms for the divergent harmonic series. We get that this is going to be the limit as n goes to infinity of, multiplied by the reciprocal, n squared divided by n squared plus 4. This limit is 1. You have to be a little bit careful. You have the limit comparison test, you have the ratio test. Make sure you remember what the limit says. For the limit comparison test, if the limit is any finite positive number, like 1, then this series behaves the same way as this series. So we can say that the series that looks like the absolute value of what we started with, n over n squared plus 4, diverges by the LCT with the harmonic series. So the series that we started with is not absolutely convergent because when I take the absolute value, I produce a series of terms which does not converge. So if this series converges, it's going to converge because of those alternating signs with that negative 1 to the n minus 1 out front. So take a moment and apply the alternating series test. That's the next thing to check. If it converges by the AST, then we can conclude that our series is conditionally convergent. Okay, so do that. It is conditionally convergent. So verify the alternating series test. Then I will come back and finish the computation. Okay, we've tried the ratio test. It was inconclusive. We did the limit comparison test to show that the series is not absolutely convergent. Let's do the alternating series test. So let A sub n, for the alternating series test, I'm going to let A sub n be the part that's not alternating in signs. So I mean n divided by n squared plus 4. I want to show that this is decreasing and that the limit as n goes to infinity of this expression is 0. Let me actually do that one first. So the limit as n goes to infinity of n divided by n squared plus 4 is 0 because the higher power is in the denominator. All right, we are decreasing in size. For that, I'm going to switch to that function approach. So let f of x be x divided by x squared plus 4. Let's take the derivative. Low d high is x squared plus 4 times 1. minus high d low is minus x times 2x. So overall, it's minus 2x squared all over the quantity x squared plus 4 squared. Don't need to worry about that. That's always positive. Simplifying the numerator, we get 4 minus x squared. Whenever x is greater than 2, this number is negative. So that tells us that starting with, say, n equals 3, this is a decreasing sequence, and that's good enough. So we decrease to 0. By the AST, we can conclude that the alternating series is convergent. So the alternating series is convergent, but when we make everything positive, it's divergent. So this is conditional convergence. Okay, let's look at the series whose terms are n to the 10 divided by negative 10 to the n plus 1. Jump right into the ratio test. This is going to be the limit as n goes to infinity of the absolute value of first the n plus 1 expression. So we'll have n plus 1 to the 10 divided by negative 10 to the n plus 1 plus 1. Okay. To divide by the a sub n term is to multiply by its reciprocal, kind of hard to say sometimes. And when we do that, we get negative 10 to the n plus 1 divided by n to the 10. Okay, so let's pair up like terms. This is going to be the limit as n goes to infinity. What I'm going to do is take n plus 1 to the 10th and n to the 10th and write this as n plus 1 over n to the 10th. It's not required to do it that way. You can leave it as it was, meaning you can write n plus 1 to the 10th divided by n to the 10th. You'll still get to the right answer if you realize that that ratio is going to 1. And then times, here I have negative 10 to the n plus 1. Here I have negative 10 to the n plus 1 plus 1. This whole expression will cancel with that, leaving us with just one copy of negative 10 to the 1. So that's like 1 over negative 10. As n goes to infinity, this rational expression goes to 1. So we have 1 times 1 over 10. That is a number which is less than 1. So the ratio test works here. This is telling us that our original series is absolutely convergent. For our next to last example, we are looking at terms of the form sine of 4n divided by 4 to the n. So let's try the ratio test. This will be the limit as n goes to infinity of sine of 4 times n plus 1. So I'll go ahead and write 4n plus 4 all over 4 to the n plus 1. Okay, then multiplied by the reciprocal of the a sub n term, we get 4 to the n divided by sine of 4n. Pair up like terms. This will be the limit as n goes to infinity of 4 to the n divided by 4 to the n plus 1 is going to leave us with just 1/4. And then we have these signs, which we can't really combine. So let me write sine of 4n plus 4 divided by sine of 4n. 1/4 looks okay, but this fraction here is not good. So this limit does not exist. In fact, it's not even bounded because sine can get close to 0 here in the denominator. So I can't really say very much about this fraction in general. I'm just going to say this limit does not exist. So this is an instance where the ratio test isn't going to work for us. That's okay. You're always welcome to try the ratio test. It just might not always work, and this is an example where it doesn't work. Let's check absolute convergence. What I'm going to do is take the absolute value of sine of 4n divided by 4 to the n. The sine function is bounded between -1 and 1. So when I take its absolute value, it's bounded between 0 and 1. So we go up in size if I replace this numerator with the number 1, and then the denominator is just 4 to the n, or if you prefer, this is 1 over 4 to the n, which is a convergent geometric series. So that tells us that our original series is absolutely convergent by the ordinary comparison test. So sine of 4n divided by 4 to the n is absolutely convergent by, here we apply the OCT. Okay, so we tried the ratio test. It didn't work. That's okay. We just needed to think of a different test. And the appropriate test, I think the best test to use for this series was just a nice ordinary comparison. This is our last example in this video of doing the ratio test. So here I wanted to give you an example kind of illustrating all of the elegant simplifications that you do when you set up the ratio test with these kinds of terms. So here we have 5 raised to a power, we have a factorial, and then we have this product in the denominator. So specifically, we're looking at the series whose terms look like 5 to the n times n factorial divided by the product of every odd integer or every odd whole number up to the number 2n plus 1. So let's set this up with the ratio test. We will say that this is the limit as n goes to infinity of the a sub n plus 1 term. That's going to look like 5 to the n plus 1 times n plus 1 factorial divided by all of the odd numbers up to 2 times n plus 1 plus 1. You have to be careful there to distribute the 2. So let me write 1 times 3 times 5, dot, 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 up to 2 times the number n plus 1 plus 1. Okay, so that whole expression is the term a sub n plus 1 multiplied by the reciprocal of a sub n, and we will get the product of odd numbers up to 2n plus 1 divided by 5 to the n times n factorial. I have written absolute values here because that's how the ratio test is defined, and you need it whenever your series mixes positive and negative terms. Here, everything is always positive. So on the next line, I'm going to drop the absolute values, and I'm going to start pairing up like expressions here. We really have 3 groups. We have the 5 powers, we have the factorials, and then we have this product of odd integers. So I'm going to pair them up, and as I do so, I'll try to rewrite things in a way which is more convenient. So let me come down here. This is going to be the limit as n goes to infinity. No need for absolute values here. Let me go ahead and write 5 to the n plus 1 divided by 5 to the n. In fact, I'll write 5 to the n times 5. That's what 5 to the n plus 1 is, divided by 5 to the n, just to really illustrate the cancellations that we run into with a ratio test. Let me do the factorials next. N plus 1 factorial is the number n plus 1 times n minus 1 times n minus 2, all the way down to times 3 times 2 times 1. But that can be written concisely as n plus 1 times n factorial. Then we are going to divide that by n factorial. Okay, so that's the better way to write this expression, these factorial expressions, so that we'll get some cancellation. Then for the odd powers, what I'm going to do is leave the one that has fewer terms alone. So 1 times 3 times 5, all the way up to 2n plus 1. This number here, if I distribute the 2, it's 2n plus 2 plus 1. So this would be the odd number 2n plus 3. The previous odd number is 2n plus 3 minus 2, so it's 2n plus 1. So I think the better way to present this product is to write 1 times 3 times 5 times the next to last odd number was 2n plus 1. And then we're ending this product with 2n plus 3. So there you can see what cancellation will happen. Okay, so here are the kinds of cancellations that you should look for when you're doing the ratio test. We've seen most of these, but I just wanted to really kind of lift them up with this example. These 5 to the powers, you should get some simplification there. That's going to leave us with 5. Factorials should simplify. Here I can cancel n factorial with n factorial. And then in this special product, notice that every single term in the numerator is going to cancel with all but one term in the denominator. So cancel, 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 cancel with cancel, 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 cancel. So what are we left with? Not much. If I rewrite this now, getting rid of the things that we wiped out. In the numerator, the only thing I have left is 5 times n plus 1. I'll write that as 5n plus 5. In the denominator, we canceled out everything except 2n plus 3. So we really simplified this expression. That's a rational expression with the same highest power in the numerator and denominator. So as n goes to infinity, it goes to the coefficients 5 over 2. That's a number which is bigger than 1. So that tells us, by the ratio test, that our original series was divergent. Okay, so that wraps up our last example. I hope you enjoyed seeing these computations. Again, I think with practice and developing an instinct to look for certain kinds of cancellation, the ratio test is a pretty fun test to apply.